Section 5.2 on exponential functions and graphs. Our objectives are to graph exponential equations and exponential functions, and to solve applied problems involving exponential functions and their graphs. So, quick review. We've got some properties of exponents here. So we're going to use P and Q being rational numbers. Those are the values for our exponents here. And then the bases, A and B, are just any non-zero real number. So the properties of our exponents start with B to the P times B to the Q. If I multiply them, I need to add their powers. So the result is going to be B to the P plus Q. If I have B to the P divided by B to the Q, the result's going to need to have their exponents subtracted. So the result is going to be B to the P minus Q. If I have A, B to the power Q, that power is going to be applied to both parts of the product. So we're going to have A to the Q, B to the Q. And if we have the quotient A over B to the P, that power P is going to be applied to both parts of the quotient. So we'll have A to the P over B to the P. And last, if we have B to the P to the Q, those two powers are going to multiply, and we'll have B to the P times Q. All right, topic 1, graphing exponential functions. Exponential functions are especially useful for modeling growth or decay over time, but they have many other uses, and we can apply them once we learn more about their general forms. The function f of x equals a to the x here, where x is any real number and a is a base that is greater than 0 but not equal to 1. It's called the exponential function with base a. And exponentials have domains of all real numbers, but limited ranges. In general, the functions come in two main shapes. We're going to have our growth shape, and that growth shape is going to happen when that base a is larger than 1. And we're going to have our decay shape, and decay shape is going to happen when that base a is between 0 and 1. If f of x equals 2 to the x power and g of x equals 1/2 to the x power, fill in the remaining values and label the graphs. So the f of x function, this is our 2 to the x function. The bottom half's been filled in. So 2 to the 0 power is 1, 2 to the first power is 2, 2 to the second power is 4, and 2 to the third power is 8. For -1, 2 to the -1 power is 1/2. 2 to the -2 power is 1 over 2 squared, so 1 over 4. 2 to the -3 is 1 over 2 cubed, or 1 over 8. For the g of x function, we're going to take 1/2 to the x power. Starting with 0, anything raised to the 0 power is 1, so 1/2 to the 0 is 1. 1/2 to the first power is 1/2. 1/2 squared is 1/4. 1/2 cubed is 1/8. When I get to the negative powers, it's going to flip the fraction. So 1/2 to the -1 is going to be 2. 1/2 to the -2, 2 squared is 4. 1/2 to the -3, 2 to the third is 8. The two graphs are shown over here. So my f of x function is already graphed on this side here. And the g of x function is already graphed with the dashed line here. What do you notice about the graphs of f and g and each of their bases, i.e. the exponential function's multiplier? So we should notice that these two graphs are symmetric reflections across the y-axis. because their bases are reciprocals. 2 and 1/2 are reciprocals. All right, example 2, using this graph on decimals. Investigate the effects of the multiplier on the size of the exponential function's output value. If you type in this link here, it'll pop up this decimals graph. We just have a slider here that's going to show us the effects of A. So what happens as we let the base A drop towards 0? So we get closer to 1, we're going to see the graph flip. As we get closer to 0, it gets steeper on the left-hand side. Larger than 1, we're on the right-hand side, like the f of x graph. Less than 1, the graph is tall on the left-hand side, similar to the g of x function. So we observe that we have exponential growth for A values larger than 1. And this is a semicolon there. And we also notice that larger values of A tend toward higher growth. And we're going to have that exponential decay. If that value of A is between 0 and 1. And we'll notice that for smaller A closer to 0, we have steeper decay or sharper decay. The word higher is hard to use in that context, but higher growth or higher decay also would apply. Okay. General graph shape. So if the A value is between 0 and 1, that's going to correspond with our exponential decay shape here. The general graph shape is going to be a decreasing exponential shape. And the end behavior is going to be that as x approaches infinity, so that's the right end, f of x is approaching 0. We have that horizontal asymptote down here at 0. As x approaches negative infinity, that's the right, the output values grow infinitely large. Application examples for exponential decay include things like half-life and radioactive decay, medication is part of radioactive decay or just decay. And then another example would be temperature cooling models. On the other side, if A is greater than 1, it's going to be our exponential growth model. Exponential growth models look like this. For them, as x approaches positive infinity, so on the right side, the output values get very large. They approach positive infinity. And as x approaches negative infinity, left side there, the output values drop towards 0. They approach 0. Examples are doubling time, and things like population growth and compound interest. Topic 2, application. Compound interest is a financial invention that became possible in Europe after the adoption of Indo-Arabic numerals, as opposed to the old Roman numerals that didn't have the benefit of zero. Compound interest can be defined by this formula, where A is the amount of money after an amount of time, P is the principal, after T years, with interest rate R, and compounded N times per year. So this is a finite compounding formula. The important piece about knowing when to use this particular formula is it's for compounding N times in a year, and that number of compoundings, N, shows up in 2 spots in this equation. So taking a look at an example here. If I invest $3,000 into a bank account, that's my principal for this investment, $3,000, into a bank account that earns an interest rate of 2.55%, so 0.0255 is my rate. It's compounded quarterly. So if I'm compounded quarterly, that's going to be 4 times in a year. So the N value is 4. Quarterly means 4 times per year. How much will be in the account after 2 years, 5 years, and 50 years? So T is going to be 2, 5, and 50. So T is changing. Since T is changing, I'm going to start writing this equation as a function. A of T. The principal is always 3,000 times 1 plus the interest rate R, 0.0255, over the N value of 4 to the 4 times T. Let's enter this function and take a look at its graph. $3,000 times 1 plus 0.0255 over 4 to the power 4 times T. I need to zoom out on this a ways because 3,000 is the y-intercept. It's the initial deposit. Instead of manually zooming, let's rescale this so that my y-axis goes up to, say, 5,000. And we know we need to see at least 50 years. Let me go ahead and make this an input of 75. And I need to see a little bit higher, it looks like, on the year scale here. Okay, so I've got a little graph of my function. I can see it as exponential growth, and I can see the graph here. I don't need to see the graph, but it is useful, I think, to be able to relate what we've written here for the equation of compound interest with an exponential function. This is the shape of exponential growth that we're used to seeing here. And now we're going to evaluate this for 2 years. So I'm going to plug 2 in for time. We're going to evaluate this for 5 years. And we're going to evaluate this for 50 years. So A of 2, after 2 years, the account has $3,156.46. A of 5, after 5 years, the account has $3,406.58. And A of 50. After 50 years, the account would have $10,692.74. Okay. If we invest $1 now at a rate of 100%, so the $1 that we're investing now is the 1, it's invisible right here, for P. at a rate of 100%, that would be a rate of 1, for 1 year. 1 year would be a times 1 for the year value right here. We end up with a simplified relationship, 1 plus 1 over n to the n. And this means that our amount earned depends only on the number of compoundings per year. So if we allow n to get incredibly large, we can find a pattern for how the number of compoundings is going to affect the amount. So let's do, as a function, a of n equals 1 plus 1 over n to the, oops, I gotta put that on the outside, to the nth. All right, now this function does not look exponential, and that's okay. It's because I've got the variable in the denominator as well. It's part rational. But what we want to see from it is when I plug values in, such as 1 compounding, I would have $1 into $2, or 2 compounding, so I get the 225. I'm getting the same values that show up in this chart, just verifying what's happening here. 3, 4, 5. We're going to skip to 100 compoundings, or 365 compoundings for daily, or 8,760 compoundings for hourly. We can continue to increase this and go for, say, 10,000 compoundings or 100,000 compoundings. And what we notice about this number is that it doesn't get a whole lot bigger. If I go for 1,000,000 compoundings, it's not a whole lot different than it was for 100,000 compoundings, even though I increased by 10 times as many compoundings. That number might look familiar. The number that we're approaching is Euler's number E, and that's the number that we're getting very close to right here. And so what this here demonstrates is that no matter what, if you increase the number of compoundings to an infinite number of compoundings, you'll never exceed the value E. Okay. So Euler's number, which is approximately 2.718. There's a lot more decimal places behind it, but we can approximate it as about 2.718, etc. It's an important number. It's irrational like pi, gets its own number and name in the calculator. Turns out Euler's number is very common and important. It's even called natural exponential base. And so for finance, it's the base for computing continuous compounding, interest that compounds all the time. And biology, it's the base for population growth curves, and it pops up all the time in the wild. So take a look at the next example. There's a function here that's given to us for v of t. Notice that e is the base of this exponential function. This gives the value of a stock, where v is the value in dollars at time t in months. So this function, v of t, is equal to 58 times 1 minus e raised to the negative 1.1t plus 20. Need to rescale this just to increase that height here, make it 100 to start. And I probably want to increase time as well. Think about this in terms of months. Let's go for 2 years. So let's go for 24. Okay, interesting shape on this graph right here. Now, they did ask me to graph the value of the stock over 1 year, so I did do 2. Let me just trim this back to look at this for 1 year. I'm going to cut it down to look specifically between 0 and 12 for 1 year. All right, so I can see my graph, and 20 seems to be the height at 0. And it looks like this is never getting above 80. There seems to be a horizontal asymptote on this graph. And right here we're at 12 months. Right here we're at 0. So a quick little sketch should include labeling on both axes. All right, so we want to use the table to find v of 1, 2, 4, 6, and 12. So we want to evaluate the function v at the x1 inputs of 1, 2, 4, 6, and 12. So v of 1 is 58.69. There we go. So after 1 month, the stock value is $58.69. V of 2 would be 71.57, value after 2 months. V of 4, the value is 77.29 after 4 months. V of 6, the value is $77.92 after 6 months. In V of 12 is $77.9999 after 12 months. So when I was looking at this graph, I did a rough estimate that 80 was going to be the top that I would need to graph. Looks like from the data, it's actually a little tighter. I don't think I'm going to really get above 78. So I've got that new supposition after actually plugging in some values that 78 might be the highest value that this graph ever achieves. It's not gone above 78. I could test that theory with a few more values. Let's go a year and a half, or a year and 3 months, I should say. A year and a half. Ooh, see, it's not quite 78 itself, but it's rounded up that far because of decimal place able to show. It's probably got a few more 0.999s after it. But 78 looks like our actual upper limit right here. So I'm going to make a little note to the side. They didn't ask me for it, but we're going to observe. There seems to be an upper limit of approximately $78. Okay. All right. So next, we were asked to use the graph of the function to predict when the value of the stock will be $75. That's an output value. So on my graph, I need to find out where y equals 75 is going to intersect. So I'm going to graph as an output value 75. Happens here, 2.69, comma 75. So we would predict after 2.69 months, the value was $75. Now, if we were to solve for this algebraically, it would be difficult since I would need to solve for an exponent in an exponential function. It is going to require the use of logarithms to do so. We're going to be working on those later in this chapter. So at this point, we're not quite ready to do this algebraically. It would require the use of logarithms. But before we talk about those, we can certainly do it graphically.